Good afternoon, everybody, and thanks for coming to our seminars. Today we have the pleasure to have here a good friend of mine. He is Apostolous Christou, Tolis for the closers, and we have an old link because we had the same PhD supervisor, Carl Murray. And so that's forever, huh? I cannot change that.
Yeah.
And now he is, I don't know how to call it, he's an astronomer or a senior researcher at Armagh Observatory in Northern Ireland. And recently I saw he giving a seminar in a meeting, and the subject was very nice, the presentation. So I invited him to give us this kind of subject seminar. And here in the Grupo, we have some people that have already worked with coorbitals, and we are at this moment doing some research on that too. And so I think the subject is perfect. And so thanks for accepting the invitation, and the podium is yours.
Yeah. Okay. All right then. Thanks, Otton, and thanks for inviting me to give this talk. So, as Otton said, my name is Apostolous Christou. I work at the Armagh Observatory and Planetarium in Northern Ireland. And well, I'm going to talk to you about coorbitals, the theory of coorbital motion, and also some application. And I would like to start with my choice of title. I've subtitled my presentation "A Guided Tour of the Coorbital Zoo." This because I think that the last 25 years or so have really opened our eyes in the rich variety that one can find in the coorbital structure. So I've drawn an analogy, if you like, between the different exotic beasts in a zoo and the, if you like, strange-looking coorbital modes. And you can see, for example, in the motion of asteroids. So the structure of my talk is, first of all, I'm going to take you on a guided tour of the zoo, a tour of the zoo to show you some of these wild beasts. Here I use the word menagerie, which is really what I used in the previous talk that Otton mentioned, and I forgot to change it. So I've already made one mistake here. I hope I don't. I haven't made more. Then I'm going to introduce a theoretical framework by which the coorbital motion at arbitrary eccentricity and inclination can be understood. And finally, I'm going to go back and apply the model to the examples I showed you in the beginning. So I'm going to start the tour with 588 Achilles. This was the first Jupiter Trojan to be discovered back in 1906, so more than 100 years ago. And observationally, it was probably the most significant find in this field because it showed that the work of Lagrange and also Euler before him had applications in the natural world. Now, of course, we know of over, I think the latest count is 11,000 Trojans of Jupiter and counting. A different type of coorbital that we are well familiar with is the horseshoe. The horseshoe was first described in a paper published by Brown in Monthly Notices in 1911, and that was actually 5 years after Achilles was discovered. And you can see how the observational discovery leads to renewed interest by the theoreticians to explore the dynamics. We saw a real-life manifestation of a horseshoe some 70 years after Brown published his paper. That was when the Voyager 2 spacecraft flew by the Saturn system and showed that two moons, Janus and Epimetheus, were in a mutual horseshoe configuration. And that was a confirmation of a prediction I believe was by Stephen Larson and colleagues based on past observations from 1966 onwards. Now, I don't have a movie of Janus and Epimetheus to show you, but instead I have a movie of a horseshoe, a horseshoe of the Earth. Now, you can see that, you can see the characteristic behavior of the horseshoe in that there is an opening at the location of the planet, in this case, the Earth. I should also say that in all these simulations that I'm showing you, I'm including a full model of the solar system. So all 8 major planets in addition to the secondary planet. Right, so here's another guy. Sorry, 3753 Crutney. This asteroid featured in a paper published, in a letter published in Nature in 1997 by Paul Wiegert et al. The authors refer to it as a horseshoe, but it's not an ordinary horseshoe. As you can see, the opening of the horseshoe is not where you would expect it at the planet, but it is instead at L5. So is this a horseshoe? Is this not a horseshoe? What's going on? There's something that we need to understand there. Just a minute. Oh yeah, so this paper and another one that accompanied it in astronomical journal piqued the interest of many dynamicists. One of them was my friend and colleague Fatih Namouni, who is now at Nice. At the time, Fatih was doing a postdoc at Queen Mary, so that's how I came to know him. I was on the last year of my PhD. at the time. And just to cut the long story short, Fatih sat down and worked out a model that explains this type of motion in the one-to-one resonance, and also many others. And also we collaborated in a physical review letter to show to demonstrate the dynamics in the population of near-Earth asteroids. Now, there are many other theoretical constructs that have been applied to the same problem since then. If I were to try to sell Fatih's model to others that are not familiar with it, I would say that, first of all, the theory is exact in the sense that it does not involve any approximations in the perturbing potential. And secondly, and more importantly, in my opinion, it is relatively easy to implement in numerical code. Now, before I go into the theoretical modeling, I want to show you two more of these wild beasts, these exotic librations in the motion of real asteroids. So here we have an asteroid, 2020 XL5. This asteroid has been advertised recently as the second Trojan of the Earth. The first one was 2010 TK7 that was discovered more than 10 years ago. If you look carefully, you'll see that the asteroid executes some sort of libration, but there's something wrong with this libration. It does not go around the L4 or equilibrium point, but instead it appears to librate around some imaginary point off to the left. So what's going on here? We want to understand this. And finally, here's another horseshoe. This is an asteroid Kamo Olewa. And you will see that as we go into the 1930s, it goes out of the horseshoe and into a loop around the Earth. And it executes several loops, and at some point, it goes back into the horseshoe like nothing has happened. Again, question marks. How can we understand this type of motion? Okay, so this takes us to the second part of the talk, the theoretical modeling. Now, to understand the theory, some of the tools that we need are already embedded within the simplest possible problem in orbital mechanics, which is Keplerian motion, the two-body problem. So here on the left, I show a planet in a circular orbit and an asteroid in brown going around the sun. Now, the two objects have very similar orbits, but they are not exactly the same. So I've given the asteroid a little bit of eccentricity. Now, if I take this motion and I translate it to the rotating frame on the right, so this is the frame that is rotating with the mean angular velocity of the planet, you'll see that the Keplerian motion of the asteroid turns into a closed loop around an imaginary center that is fixed. Now, I'm going to call this loop the epicycle, and the center of the loop I'm going to call the guiding center. And in the next slide, I'm going to give Earth a mass and activate the three body problem dynamics. Okay, so right, so here I have a movie on the right-hand side of the slide. I'm going to show you a horseshoe asteroid of the Earth. So the asteroid is going to enter the frame of the movie from the bottom left. It's going to approach the Earth. It's going to complete the, if you like, the horn of the horseshoe and go back the way it came. And I show separately the position of the asteroid along the epicycle as a diamond. And I show the position of the guiding center as a square. So I'm going to start the movie now. So you see how the Earth does a little epicycle of its own because it has a small eccentricity as well. And you can see how the asteroid comes in. It keeps approaching the Earth. It's closer, but now the guiding center begins to slow down, and at some point it will stop and then reverse itself and go back the other way. And the point I want to make here is that the dynamics that we're interested in other words, the horseshoe, are encapsulated in the guiding center, and the epicycle is just along for the ride. Okay, now that there are actually three components of the motion of the dynamics in orbital motion. There is also the secular evolution of the orbit, and this is embedded in the variation of the eccentricity and the inclination vectors. Now, for most applications, we can make the assumption that the time scale for all three types of motion are well separated. In other words, the epicycle gyrates much faster than the guiding center, which itself evolves much faster than secular perturbations. Now, this actually leads to the central idea behind Fatih's model, in that under these assumptions, we can take the Jacobi integral and average it over the epicycle, the fast epicyclic frequency. When we do that, we derive the expression that you see in the center, where the quantity S is the integral that you see on the top, where everything except lambda r can be considered a fixed parameter. Okay, and now the integral looks rather formidable, but it's actually quite straightforward to evaluate, because all the quantities in the integral can be written down in terms of two-body formulae for the orbital elements. Okay, right now, yes, how do we use this to explore the dynamics? Okay, now this expression has the form of an energy conservation type law. So the S term can be thought of as a potential energy. The A squared on the left-hand side is the kinetic energy, and there's also a conserved total energy that is represented by the constant C. Now, because we have a squared in the left-hand side, this quantity can never be negative, and therefore, if we set A to 0, we can obtain bounds to the motion. In other words, we're able to say where the guiding center can and cannot go. Now, I'm going to illustrate this by plotting the potential S for a near circular and near planar orbit. So this is represented here by the blue line. And it's expressed as a function of lambda r, which is the position of the particle along the unit circle relative to the planet. Now, if the energy C is okay, let me express this in a different way. So the particle can go anywhere where the total energy C is higher than S. So, for example, if C is lower than the value of S at L3, then the motion is constrained to librate around L4 or L5. If C is higher than the quantity on the value of S at L3, then the particle can go anywhere except very close to the planet. And this is essentially the horseshoe configuration. Okay, now I'm going to show you what happens to the potential as we increase the eccentricity. Okay, so here I'm going to show you a movie that I take the eccentricity from 0 to some quite high value. I think it's 0.7 or 0.8. So here we go. What you see is that as the eccentricity increases, there's a kind of bifurcation. And instead of 2 local minima in the profile, we now have a third one at 0, which is the location of the planet. Now, this means that we can, apart from the horseshoe and the tadpole, we can also have a third type of motion, which we call the quasi-satellite. oh yes, yes. So yes, and I'm going to say something about the physical meaning behind these singularities on either side of zero. So why do these singularities exist in the potential? Well, in a word, these are the collision singularities. So as you increase the eccentricity of the particle, you essentially increase the size of the epicycle. Now, for any eccentricity, there are two values of lambda, which is a location of the guiding center, in which the epicycle just touches on the planet, and therefore it is certain that the particle will collide with the planet. And we're going to see what happens when what happens to that picture when I also give the orbit an inclination as well. All right, so okay, this is another point that I want to make about eccentric orbitals. This is something that you may have noticed in my previous movie, but I'm emphasizing it here by indicating the locations of the L4 and L5 equilibrium points. So I'm going to start the movie again, and what you're going to see is that the potential minima move away from the equilibrium points and towards L3. And this is another one, if you like, of the key characteristics of eccentric orbits. Okay, now what I've done, I've taken the eccentric orbit and I've given it an inclination. The first thing that you might notice is that there are no singularities anymore. The singularities have turned into maxima with finite values. Now, I'm going to give, I'm going to call this the two towers. If any of you are fans of Lord of the Rings, it will be really easy to remember this term. Okay, so now, in this case, I have fixed both the eccentricity and inclination, and the only other orbital parameter that I can play with is the argument of pericenter. So I'm going to play this as a movie, going through all possible values of omega, little omega. So here we go. 90, 180, 270, 360. Now, yes, the other point I want to make is that the perturbing function is pi periodic. So whatever happens between omega of 0 and 180 also happens between 180 and 360. Okay, so what do we see here? Well, we see actually two things. The two towers are generally not symmetric. They don't have the same height, except when omega goes through 0 and 180 degrees. And there are also values of omega where the two towers turn back into singularities. Now, why does this happen? Well, let's go back to the geometry of the orbits. So here we have, again, the same configuration. Now, apologies for my poor drawing skills. I have inadvertently made epicycle look like an Easter egg. But what I want to show here is that now part of the epicycle is below the plane of the planetary orbit, and the other part is above the planetary orbit. And if you look on the left here, for values of omega near 0 and 180, the nodes are near the apsis, the perihelion and aphelion. So in this configuration, the epicycle can pass right through the planet's position without a collision. However, in the configuration I show on the right-hand side, where omega is close to plus or minus 90 degrees, the nodes are very close to the unit circle. So there you can have a collision. However, now you can only have a collision for particular values of omega. So generally, the collision singularity is removed, and we can have stable orbits, coorbital with the Earth, even when the location of the guiding center puts the asteroid very close to the Earth's position on the planetary plane. Okay, so so this is a summary of what of the different types of coorbital motion that we can have for eccentric and inclined orbit. So apart from the three types that I have already mentioned, because now the two towers are not of equal height, the particle could have enough energy to clear one tower but not the other. And this gives rise to what I call an asymmetric horseshoe configuration, where the opening of the horseshoe is not at the planet, but instead at either L4 or either the location of L4 or L5. Well, actually, the maxima are not always at the locations of L4 and L5, but for significant eccentricities and inclination, they usually are close to them. Finally, you can have a type of orbit that is so energetic. This is the range that I represent in yellow, where it can clear both towers and does not enter into any sort of libration. We call this the passing orbit. Right, okay, so this is a figure from Fatih's Icarus 1999 Icarus papers. It shows such an asymmetric horseshoe in the guiding center coordinates, AR and lambda R. What I want to make, the point that I want to make here is that you can think of these coorbital modes as, if you like, as the joining up of any two of three fundamental librations. So one is the horseshoe, the second is the tadpole, and the third is the the quasi-satellite. For example, here we have the joining up of a quasi-satellite and a horseshoe, and the term that we have used in those papers for this type of motion is a compound mode. All right, so now that's a bit more to say about coorbital dynamics at eccentric and inclined orbits. Here I have an orbit like before, which is eccentric and inclined, with a difference that here the eccentricity is higher than the inclination is higher than the eccentricity. So, for example, the inclination can be 30 degrees or 0.5 radians, and the eccentricity could be 0.2 or 0.3. Now, this profile here is different than what I showed you before, because there's only a single minimum at 0. There are no two towers. If I now go through all possible ranges of omega, like I did previously, you'll see, right, so you'll see that the value of the potential at 0 goes through an inflection for a certain value of omega. This is usually around 30 or 40 degrees. And it turns back into the two-tower configuration. So in the general case, now we can separate, if you like, two types of behavior. One where the potential has two maxima, the two towers for all values of omega, or orbits that have very high inclination and moderate eccentricity, where there's only one maximum for in the vicinity of omega equals 0, but as you move away from 0, you go back into the two-tower configuration. Now, in practical terms, this does not make much difference in the dynamical evolution of asteroids, of orbital asteroids, because omega tends to circulate through all possible values. But one case where it might matter is if the asteroid is in a quasi-resonance, which locks omega to librate around 0, and then for those orbits, you might not be able to recover the two-tower configuration, meaning that you can have a horseshoe, but not a quasi-satellite. Okay, so let's see what else. Oh yes, right. So far I've talked about asteroids that have, if you like, small to moderate eccentricities and possibly quite high inclinations. But also there is a slight qualitative change in the type of motion when both the eccentricity and the inclination are high. This happens, for example, when you have an asteroid coming to near Earth space from one of the high inclination families, and it's still not decoupled from the main belt, so that the aphelion is still above 2AU, say. Now, for these types of orbit, what happens is that if you like, the two towers still exists, but their energy is lower than that of L3 that you see on either edge of the profile here. Now, this means that it's impossible for the asteroid to go into Horseshoe. If it exits either the quasi-satellite or the tadpole configuration, it goes into a compound mode, but a compound that involves quasi-satellites and tadpoles. Okay, so no, not quasi-satellites and horseshoes. If the energy is even higher, so that the asteroid can clear both towers, you enter into a mode that, well, it's been, if you like, informally called the Mickey Mouse mode. And I'm going to explain what that means in the next couple of slides. Okay, right, so, okay, theory over. I'm going to go back and apply the model to the asteroids I showed you before. Let's start with the horseshoe. So here on the left, I show you the simulation I showed you before. And on the right, I plot the potential again, but now in polar coordinates, not in orthogonal coordinates. And I'm doing this so that it's easier for you to compare how the model performs against the simulation. So here, the potential profile is again the blue line, and I've chosen to fill it with a blue color. The dashed circle and the red dot are the energy and the location of the asteroid at any one time from the osculating orbit. All right, now I'm going to start with animation, and you're going to see, right, so the asteroid does not have a high enough energy to clear the, if you like, the maximum of the potential at zero, so it ends up bouncing off on either side, and this creates the horseshoe that you see on the left. Right. Oh yes, I forgot to mention here that the blue lines indicate the directions of L4 and L5 equilibrium points. The second case, we have our Trojan. Now, this is quite an eccentric orbit. You can see the two tower configuration is quite pronounced. The two towers are quite high. So if I start the simulation, you see how the object is constrained to librate between the tower near L4 and the potential maximum at L3, and this explains why the center of libration is not at L4. Then we go back to our one of our favorite asteroids, 3753 Critney. Here what we see is that again we have the two tower configuration on the right there, but the two towers are very asymmetric. So one tower is much higher than the other. Oops, sorry. Okay. So the asteroid has enough energy to clear one of the towers, but not quite enough to clear the other, and this results in it bouncing off the tower near L5 and gives rise to this asymmetric horseshoe. Now, if you follow the evolution of this asteroid over some hundreds of thousands of years, you found that it enters into a variety of coorbital modes. These are some of these here, including compound modes. In particular, I want to draw your attention to these three here, which are compounds formed by joining up a tadpole with the quasi-satellite, especially for the one on the upper right there. This is the only symmetric compound mode that we know of. So what happens there is that the quasi-satellite joins up with both the L4 and L5 tadpoles and creates this characteristic shape. Now, I remember showing this to Carl Murray when I was actually writing this paper. Carl is good at coining new terms for things, and he called it the Mickey Mouse resonance, but somehow the term didn't catch on. Well, we can't have everything. Okay, now this is our last example. This is asteroid Kamo Oalewa. So I'm studying the movie, and you see what you see is that the asteroid is captured into a quasi-satellite mode, and as soon as that happens, the two towers rise to lock it in, and then after a while they drop again to let it go. Now, this is not a coincidence. This has to do with a dynamical phenomenon that was studied in Fatih's 1999 Icarus paper, and it has to do with the evolution of the argument of pericenter. So in the next slide, I'm going to show you the potential profile again on the left. Just a minute. Yes. And then on the right here, I'm showing you the evolution of omega for the same time period. And what you're hopefully going to see, oops, sorry. I'm very bad at this. Yeah, so as soon that the asteroid goes into the quasi-satellite mode, the argument of pericenter begins to regress, right? It becomes smaller with time. It goes through minus 90 degrees, which corresponds to the double singularity configuration. And then when the particle is released back into the horseshoe, omega starts to precess again, although at a much lower yet positive rate. So in a sense, here the quasi-satellite mode assumes control of omega, and then releases that control upon exit from the quasi-satellite. And what I showed you is actually part of a cycle, which Fatih showed that it can happen any number of times in the context of the three-body problem. So the particle would alternate between horseshoe and quasi-satellite for any number of times. Now, a question here is what happens if, apart from the two masses in the three-body problem, we also add the other planets? And the answer is that the cycle might actually persist for some time, like, for example, for an asteroid I show here with the multicolored plot. This is an integration from a different paper of this asteroid, where they use all 8 planets in the perturbing potential. Now, eventually, what will happen is, because the planets force their own secular perturbations on the asteroid, eventually the asteroid will exit that cycle and go to some other coorbital mode. And if you follow the evolution of most of these asteroids, with time, you see that this is what they typically do. They go from one mode into another for as long as the same major axis is within a Hill sphere of the Earth. One other mechanism that can extract the asteroid from a particular coorbital mode is if there is an encounter with Venus, for instance, or Mars. So, right. What was it? Yes. So I just want to finish the presentation by saying a few words on quasi-satellites, of which we have heard a lot about in the last 20 years. Well, actually, for as long as we know that there are modes in the coorbital resonance apart from the horseshoe and the tadpole. Now, in fact, quasi-satellites are almost as old as horseshoes. A type of quasi-satellite appears in a paper that was published in Monthly Notices in 1913 by a guy called Jackson. So that was 2 years after Brown published his papers on horseshoes. Jackson calls them eccentric retrograde satellites. However, nowadays, because there is a possibility for confusion with the distant satellites of the giant planets, we call them quasi-satellites to make the distinction. Also, Michel Henault has worked on quasi-satellites. He's shown in a paper with Guyot in 1974 that actually they're conditionally stable for small mass ratios, and in this sense they are similar to tadpole orbits, which are also conditionally stable on the mass ratio. Now, we can distinguish between different types of quasi-satellites. So if your asteroid has an energy that is just large enough to clear the potential minimum, then this is a quasi-satellite with a vanishing libration amplitude. So in practice, the guiding center is just a fixed point at the location of the planet, and the Cartesian motion of the asteroid is identical to the motion along the epicycle. And these are in fact the types of quasi-satellites that Jackson worked on. Now, if the energy is higher than this minimum, you also get, apart from the epicycle, you also get a guiding center libration with a finite width. So in practice, what you see is really an epicycle that goes up and down until, of course, the secular evolution will cause the asteroid to exit the quasi-satellite mode. Now, like some solutions of the three-body problem, the quasi-satellite has been used in astrodynamics at least once before. There was this mission called Phobos 2 back in 1989 that was flown by the former Soviet Union. And the idea is to approach the Martian moon Phobos, to map it, and after that to land on the surface. And the trajectory engineers actually used a quasi-satellite of the Jackson type as a way to map the orbit and cover the entire surface of Phobos. Now, I believe there's another mission now that I believe is to be flown by JAXA in 2024, I think. It's called MMX, and it's going to repeat the Phobos 2 profile, and in addition try to return samples of Phobos to Earth. And this mission also makes considerable use of the quasi-satellite dynamics because it's such a convenient tool to map small moons from planetary orbit. Okay, I think this is what I wanted to say. So this is my summary, and I was looking for a nice quotation to finish this presentation with, and I found the following by Peter Goldreich in a 1997 book about rings. And the quotation goes, "Don't worry about Newton's equations. Most people do not realize how many solutions they have." And I think that this encapsulates rather well what I have just showed you. So that's it. Thanks very much for your attention.
Thanks very much, Doris. Fantastic presentation, very interesting. And well, I have some questions, but let's see if anybody would like to make any questions. It's open for questions or comments.
Yes, fire away. Figuratively speaking, of course.
Okay.
Just a minute. Okay, so Sylvia has
Hi.
raised a hand.
No, I don't have a question.
Okay.
Very, very nice talk. You gave me some ideas, and very interesting. And I'd like just to say hello to you.
Hey. Hello, hello.
Thank you.
If you use your ideas for commercial purposes, I would like to ask for a percentage.
Royalties.
Okay.
That's it.
Thank you again.
Very nice to see you, Sylvia.
Very nice to see you too.
Okay.
Indeed.
Anybody else? Any comment, any question? Okay, I have some. I have a few.
Okay. Go ahead.
When you compare inclination with eccentricity, what units are using? What's the, when you say eccentricity equals inclination, what means that?
Okay, let's go back to this is really okay. Yeah, so this is really interesting. Now, I showed this, if you like, phase diagram here.
Yeah.
Here, what I do, I compare the inclination in radians with the eccentricity.
And match one to, you find, so the division is actually the same when using radians.
If it's not exactly at 1, it's very close to 1, and I would have expected that instead of I and E, what I should be using is the, if you like, the
strength of the coefficients.
The Delaunay momenta that correspond to E and I. So 1 minus square root of 1 minus E squared, and the corresponding momentum that involves the cos of the inclination. I have not tried that yet. Now, when Fatih wrote his Icarus paper, he made an approximation that basically the model that he used in the paper is truncated to order 2 in the eccentricity and inclination, right? And then in the physical review letters, he uses the essentially a semi-analytical model with the full potential. In the Icarus paper, he says that when you use the full potential, you have to replace I and E with the corresponding Delaunay momenta. But what I find that even for orbits with significant eccentricity and inclination, the agreement, if you like, with the second order theory is still quite good.
That's good.
Yeah,
That's
this is something that needs to be investigated more, and I'm ashamed to say in the 25 years that have elapsed since those papers, I haven't done it yet.
Too much things to do. Okay.
Well, yes,
okay.
well, yeah.
Okay, another one about routine.
Yes.
Could you show in the last movie that you showed the routine?
Just a minute. This one,
yeah.
is it?
Yes,
okay,
yes.
Should I show it again?
Okay.
Okay. Oops. No. I have to go back into presentation mode. Just a minute. Let me see. Am I still sharing?
Yes.
Okay. I'll just go back into presentation mode. All right. I'm not good at this. All right. There you go. There you go. And we exit the quad satellite, and this changes the rate of change of omega. Amazing, isn't it?
Yeah. Well, the question I have is how it's good to have the two plots, because my question is, how long does it stay as a quad satellite? I mean, if it's a short time, long time, that has something to do with this plot on the right. So the time it takes to change that regression in the percenter. So if you want to, someone wants to compute how long is it going to stay as a quasi-satellite, the idea is to compute the secular variation of the percenter.
Yes, the argument of the percenter is key. So all you have to do really is compute the heights of the two towers as a function of time, and then when the heights are lower than the energy of the orbit, then the quasi-satellite will cease.
Okay.
There are actually many other cycles like this one, which are actually involve more phases. So there's a cycle that goes from a horseshoe to an asymmetric horseshoe, a quasi-satellite, back to an asymmetric horseshoe, and finally back to a asymmetric horseshoe.
Okay, this plot, this movie you are showing is for which satellite, which asteroids?
Asteroid, this one, 469. 219. Yes.
I had asked. I made my question about that, but I asked about creatine.
Yes.
The other.
Just a minute. Yeah. Okay. There you go. Here we are.
Yeah. So the question is very simple. Is it a coincidence that the higher tower is aligned with L5, or is it common, or is it any? It's just a coincidence or not?
Okay. Well. Technically, it is a coincidence. In practice, when you see eccentricities like 0.5 or 0.6 or 0.7, the maximum will usually be close to either L4 or L5, but there is no reason for it to coincide with L4 and L5.
So it comes from the high eccentricity.
Yes, it comes from the high eccentricity.
Okay, good. And the last one is just a comment. Okay. On the last part when you discussed about the quasi-satellites. Could you you put that historical slide about the first works? Yeah. And so, yeah, the previous ones. Okay. So my question is, well, I have already studied 20 years ago this kind of trajectories, but from a different perspective.
Okay.
Not thinking about any corbitals, but studying periodic orbits.
Mm-hmm. Oh yes, yeah.
Yeah. So there's a report by Roger Brook, 1968.
Okay.
A NASA report for the Earth-Moon system. Earth-Moon system, and where he explores all possible periodic orbits he could find, the symmetric periodic orbits at that time. And there is one family of periodic orbits that I believe corresponds exactly to this one. And
yes, that's actually, yeah.
People from the space engineering side that works with celestial mechanics, they call it DRO. Distant retrograde.
Yes, I'm familiar with them. Yes, yeah. These are the same. Yeah.
Okay. I
didn't know that. Yeah. So they're all. I mean, we call the same thing with different names, and we make things too difficult for ourselves.
From orbitals to no.
That's right.
Very, very, very nice. Very nice. I didn't know that. So I think those are my points. Anybody else has a comment or a question?
Please. I don't bite. Not on Fridays anyway.
Let me tell you, a colleague of mine. Let me see if he's here. See, Professor Rodolfo Vilhena de Moraes. He asked me if he's on screen now. If you were a saint.
Helena. I don't know this person. I have never met her in my life.
He asked if you were a saint because of the name. Because of the name.
God. No. No, this is okay. Well, there's a story about the name. Because
I think
it used to be the case.
You must suffer when you were a child.
Not particularly. Well, I don't remember anyway. So yes, I mean it was the custom that the grandson who would receive the name of one of the grandparents.
I see.
And yes, whenever there was some members. Well, I've been told that some members of the family insisting that the custom be upheld. But then when my brother was born, my mom put her foot down and said, "Okay, I'm going to call it, the name that I like." So. Anyway, it's entirely coincidental. So I don't fashion myself as, I don't figure myself as some kind of emissary of Jesus Christ, rather.
Okay.
Right.
So I think that's it. Thanks very much.
Yeah, I mean,
I enjoyed a lot. I think.
If people have, if people have any other questions, even offline, you can send me an email. I don't promise to be able to answer them, but I will try.
Okay, good. Thanks very much. I think it was very, very enlightful, and I really enjoyed it. I had seen some of the works by Namoni Fati.
Yeah,
but I didn't have the patience to read and trying to really understand. I think you made it very, very easy now. I think I can go back there again. So thanks very much.
Congratulations, Ed. Very nice talk.
Thanks very much, folks.
Yeah.
Appreciate it coming from seasoned dynamicists like yourselves. All right.